Physics 211 Oscillations by Swayam Sankit Kumar Trivedi. Purpose. The purpose of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring using tracker, then comparing this data using the computational model generated from GloScript. The fundamental principles used are Newton's second law and the energy principle. The preview of the main results are: the system's total energy remains the same at zero, thus demonstrating the energy principle. The motion of the oscillator can therefore be predicted. The main physics ideas used. The energy principle. The energy principle formula, also known as the work energy principle, is a system change in energy is the sum of the work done by the surroundings and thermal energy exchange with the surroundings. The formula was used to measure the change in energy of the system. The second formula used is Newton's second law, or the momentum principle, which states that a system's change in momentum is directly proportional to the net force applied. The F net in this case is the force of the spring and gravity, hence we use this equation. Other useful formulas include: the first one is the velocity update formula, which is final velocity is equal to the initial velocity plus the change in acceleration times the change in time, while the second one is the position update formula, while the final position is equal to the initial position plus the average velocity of the object times the change in time. The rest are kinetic energy, gravitational energy, and elastic energy. Conditions for tracker and observed motion. I first kept the uploaded video onto the tracker, where I was able to determine its motion. Through this, I was able to find the initial conditions, where the mass was placed at 0.402 kg and the displacement at its initial position was negative 139.3 meters, while its velocity was 0 and the spring constant was 6.875 newtons per meter. In this case, the system was the spring, earth, and mass, while the surrounding was negligible. I then had to do some calculations in order to calculate the time period, which I was able to calculate as 1.5193 seconds. I was then able to use this time period and plug it into the formula for spring constant in order to find this spring stiffness, which was 6.875 newtons per meter. Then I was able to solve the relaxed length, which came to approximately 0.1264 meters. Using the acquired data from the tracker, I then placed them into GloScript, where I changed the ball mass to 0.402, the ball position to the vector 0, negative 139.3, while the ball velocity remained at 0, and the constants such as gravity and the spring constant and L, these were adjusted. In this case, the system was maintained as the spring, earth, and mass, while the surroundings was negligible. I then edited L, which was the ball position minus the spring's position, and through that I was able to calculate L hat. I was also able to change the kinetic energy, gravitational potential energy, and spring energy by inserting the formulas, and then in order to calculate the total energy, which was given by the addition of all of them. I then continued editing a few pieces of code, such as fgrav, which is equals to mass times acceleration acting in the y direction, hence is negative, the force due to the spring, and the total net force acting on it. I also edited the ball velocity and the ball position at a particular time, and the ball position minus spring's position in order to get L was the same as the previous code I'd done at the top. Then I was able to also calculate the energy changes as I changed I edited the GloScript by inserting these values. I then compared the results of the observed versus the computational. Through this, we are able to realize that in the beginning of time, they keep on overlapping with each other in both the x and the y direction. But as time goes on, the model has an increased change in y and further move a shift to the right for the x-axis. This is because in real life, forces act on the ball, such as air resistance, which causes this shift, and therefore the results would vary depending due to external factors acting on it. To further explain these differences, we could go to the possible sources of errors and assumptions we made. One such assumption we made was that the velocity of the ball remained constant, implying no external force such as air resistance caused any work on the ball during its motion. However, this isn't true in real-world applications, as air resistance acts on objects. The ball's motion was considered only in the x and y directions without any movement in the z direction, which may be false. Another source of error could be inaccurate placement of the center of mass when using tracker, which may lead to incorrect data, as it is really hard placing the center of mass every time at the exact position. What if? Part 1. Yes, the energy principle is satisfied. This is because no external force affecting the isolated system, hence the change in energy is 0. This can be proved because when you subtract the bottom from the top of the graph, it will equal 0. What if part 2? When we calculate the oscillation period for the x position data as 1.5193 seconds, and when we calculate the oscillation period for the y position, we get 1.534 seconds. This means that if we change the period, then there will be a change in the spring constant. Conclusion. We learned about the energy principle and that the change in system energy will always be zero unless acted on by its surroundings. We also understood that complex motions can be predicted using Newton's law of motion. Thank you.